This is my Physics 2211 Lab 3 introduction. Purpose, part 1, to find the mass of the black hole computationally based on the star's orbit and reference to it. Part 2, determining the initial velocity of a spaceship that will not make it crash into a moon orbiting a star. Our system is surroundings, so for part 1, the star is our system and the black holes are surroundings, and part 2, the spaceship and the moon are our surroundings and the star is our system. Models and principles, parallel and perpendicular force. Parallel force is going to change our velocity, and it's going to be equal to the absolute value of momentum, the absolute change in momentum. So that means that it's like the change in the absolute value of momentum. And then this will basically be the change in the direction of our object. Perpendicular, if there's no v, then there's no parallel force, and we can use these to find the force on our various objects in our computational model. Gravitational force Fg equals gmm r hat over r squared. We will use this equation to derive the mass of the black hole. Fnet will equal Fg, and Fg will equal the Fnet parallel plus our Fnet perp. Model of the model 1 mass of the black hole. So I'm going to play my video briefly of my little experiment here. These are my initial conditions. This is a constant, and this is given to us, and you just got to edit it in. So I'm not going to go over this much. So this is all procedural. I mean, like here we have the definition of Fnet is dPdt, and we derive that here. The real interesting thing, and like I said, these is all definitional. This goes back to our Fnet and Fnet our parallel and perpendicular stuff earlier. Like here, for example, we said earlier that Fnet equals dPdt parallel plus dPdt perpendicular. So we'd subtract it from Fnet to get our dPdt perp. And then here we have our derivation, and this comes from the fact that if you have dP over dt, right? dP over dt is defined as our change in momentum. So, I mean, you can just imagine that, this equals our gravity equation, and then we're just going to rearrange that for mass, and that's what happens here. Model 2, try not to crash. These are my initial conditions. These were all given, so I'm not going to go over them very much. This is my computational model. As you can see, I put my rate very high because I kind of had to, because it's really messed up and evil. So here, we just have a bunch of different repetitions of our sort of forces due to gravity on our moon and on our ship. We just separate them, and we have to do them because they're going to have interactions with one another, and they're going to affect each other's orbits, and the spaceship will actually orbit the moon while it's orbiting the star. This is an iterative loop to sort of update the velocity and position of the ship and moon. Results, I got this little comma-esque orbit. I took a screenshot of this to look kind of silly. It veers off a little bit here, and it goes off the screen, and it gets a little too big to fit on here. Possible sources of error, so rounding errors, sort of just making my mass earlier, my mass inaccurate. Too fast of a rate. I mean, if you go back, it was very, very fast, and that might lead to some inaccuracies or some issues with the look of my orbit. What does it mean? The net force and then change momentum are definitionally differ by multiplication of a scalar value if mass is constant, thus they have the same direction and magnitude. The net force is different from its parallel and perpendicular components because they're just that, components. They sum to make up the net force. What if If the imaginary system had a black hole, a star, a planet, and a moon, we would need to include the forces of each of the objects on each other. The dominant interaction would likely be from the black hole because it has a mass much larger in magnitude than the rest of the objects in the system. Thank you.